Hello everyone. So today my hackathon challenge is on the test and validation of the protocol, so industry model. So for this selection, I have taken PCI 6 bus. Uh, so the tool which I have used is VisualSim Architect tool. So since this is a system validation protocol, it's not like it's a very abstract model or those stuffs. So first, let me just walk you through this basic PCIe basics of it. So as we all know, the PCI is a high-speed bus interface. So just to give a basic overview of the things. So it's a high-speed I/O serial I/O buses. So it's a parallel bus topology. There are multiple point-to-point connections. It's a basic dual simplex channel. So it's a low voltage and multi-differential signal. So in general, differential signal means like the the pairs, the TX plus and TX minus, RX plus and RX minus. So these are differential signals. They are twisted in nature. So one carries a positive signature, and the second one has the negative charge. So they both are twisted in nature. So the reason this differential signal exists is to reduce the noise and all those stuff. So the basic transfer protocol and the basic transfer bit in this PCI bus is a FLIT. So it's a basic transfer packet. So for learning purpose and all, I have taken this from the ASIC Lab VLS Academy. So these snapshots and all. So what is a PCI? Everybody knows PCI is a peripheral component interface protocol. So in general, so we have a master, we have a slave. So in between of these two, I can have a multiple interconnects, multiple other different other different buses, other different interconnects, and all those things. So this PCI is used to connect to a external world interface. So I'm having a master as a CPU. So there is a root complex and there is a switch. So the CPU wants to transfer the or connect to a slave. Means it has to transfer to a root complex, from root complex to a switch, from switch to an endpoint. So downstream point. So this is a basic PCIe protocol layer, like software, transaction layer, data link layer, physical layer. So in this physical layer, the voltage layers and all are there. So basic PCIe, what is a lane, what is a link? So lane is this receiver. Uh, this lane is this for with respect to this. So this is a receiver lane, this is a TX. So both combining, we have a link. So here there are two lanes. So in general, the PCI internal structure is like this. So PCI 6 architecture is a FLIT mode, FM mode. So whatever signals I get, I convert it into a TLP. This is transaction layer packet. So in this, I'm having a split in nature. So there is a local prefix, header base, OHC, data payload, TLP, header. All these packets are there. So then I add and then I convert this TLP by adding ECC, CRC, and all these parts. I convert it into a FLIT. So FLIT is composed of so this FLIT is present in the data linkage. So what I do, I add a sequence number and I add a LCRC to it. So then in the physical layer, I add start point and end point packets and all. So this is the basic overview of a PCI. If you want to go in deep and depth or dive, so you can just refer to this PCI 6 protocol from ASIC Lab, VLS Academy and all. So coming to the model wise, so since this is an architecture exploration tool, we don't have in-depth details about all the PCIe and modeling and all here. So we are going to model only few of the parameters here. So one is what is the read request size bytes I'm going to model here, and flit size. So with respect to PCI 6, this is fixed flit size. So 256 byte is a fixed protocol wise. So how many lanes you can have? One lane, two lane, 4, 8, 16 lanes. So what is your lane size? That one. And the next one is a buffer size bytes. So RX and TX, what is the buffer size? Buffer. This is a variable one. So since I'm having here 1, 2, 3, 4, 5, 6, 7, 8. So I'm having since I have selected 16 things. So I have this. I have say sorry. I have there are 12 devices that I can attach here. These 12 devices can be attached. The lane concept is different. So I'm not worried this bit error rate, number of retries or timeout or anything, but I have this replay rebuffer size. So this one is the storage element. Once a transaction layer issues a transaction, we store it in uh, so we store it in a buffer. So here is the buffer. So once a device A issues, so I'm having something called retry buffer. What I do is I store my transactions all into this buffer size. So I issue on everything like for every one time minute I issue one transaction or something like that. So for example here just to give basic understanding. So this basic protocol like acknowledge and acknowledge. So at T0 I issued payload 2. So the payload 2 it went to TX channel and it received to here RX channel of the device B. So it accepted, it checked whether the payload is proper or not, whether it's a good payload fit or not. So if it is good, that means it will accept the thing, and then what will happen is it will send an acknowledgement back to the device A. So like this, the protocol happens. So payload two is correct, payload three is correct, payload four here we are saying it's not a proper flit due to some CRC bit or something. It got corrupted or something. So now what happens is at that point of time it will say it's a not acknowledged or acknowledgement is set to be NAC. So what happens is it receives STA NAC 3, STA NAC 3. So that means acknowledged bit sequence only up to 3 I have acknowledged. From 4 it did not get acknowledged. So next to fifth payload fifth payload is issued. So the same way it goes, it checks whether it is good or bad or whatever it is. If it is good, means it will be withhold there itself. It will not go. It will be not accepted unless and until uh, the there is a reissue of the fourth packet. So since this buffer will be go on issuing, so it will be accepting. So once this NAK, so here at T5 it got acknowledgement to proper T6 acknowledgement payload 3, T7 acknowledgement 3, then it stopped getting the acknowledgement unless and until this payload 4 is reissued and the acknowledgement sequence get back, it won't be proceeded further. So this is the basic protocol sequence, like how it is. So this retry buffer size, right? Only we are considering that here, replay retry buffer size. So I've kept my 1024 retry. And number of successive acknowledgement, I have kept it 3. So if you want to know more about this, so there is a help section, and here we have a basic overview of what is PCI bus, what are its key features, what is the configuration, what. So in general, so I'm using here a traffic generator. So this is my CPU. I'm just saying it as a traffic generator CPU, and there are few data structure. There's a processor data structure. So in this, what it is having is so I'm considering only few of them. So I'm saying my source name is source one, and my destination here I've considered. So in one test case, I'm going to consider it as a random device selection between one, two, three. Or here I've considered like TG1 means go only to DRAM one. So next is a command whether I want read or write. So here I'm generating 50% read or write. Even I can make it just read or write, just only read or just only write transaction. So I'm having what is the number of bytes I need to generate, what is the priority of this TG and all. So I'm just having a few parameter selections here. I'm just making it. So in device interface, it's just a model. That's it. So whatever transaction I send it through a PCI bus. From PCI bus, it is getting routed to based on the selection of the device. It is getting selected to DRAM one. So this DRAM is a slave device for me. I have not used any memory controller or anything. It's just a simple model PCI bus validation. So I'm having the CPU or GPU or anything. I've just modeled it as a TG. So it's continuously generating transactions, issuing the transactions at some traffic rate. So DRAM or RAM is my slave. So what are the parameters I'm looking at in DRAM? So what is my speed? What is my memory size of the DRAM? And DRAM is having how much is the pre-fetch time? What is the access time for the write? What is the access time for read write? What is the erase time for that? So the DRAM protocol, the DRAM protocol parameters we have taken, it is there. This is default setting, so I have used that. So what is the refresh rate cycle? So how many refresh cycles are needed? So I've not modified any of these things. I just kept this one as constant. So my technology is DDR4 and my bus width is 64 bytes. So like this, I'm having three slaves, and I'm considering three TGs here. So my main thing is to validate. So how am I going to do the validation is so I have selected uh, I have selected few test cases. So the first test case I'm considering is before going to do that. So how do you measure the throughput of PCI, or what is the PCI? So in general, the formula is the bandwidth into overhead into number of heads. In general, overhead means I'm having here 128 bits by 130 bits encoding. So 128 bits is converted to 130 bits, or 1 byte by 1 byte. So like this, for each generation, there is an encoding format. Some are having NRZ, some are having PAM, like this electrical encoding. So I'm having that overhead. What is that overhead? So here I've taken 1B, 1B, and number of lines. What is your this? So the throughput. In general, I'm saying PCI 6 means 64 giga transfer per second into 16 divided by it. So I get 128 GB per second is the ideal throughput or ideal bandwidth that has to be achieved by the PCI for each TX. So coming to the test case scenarios and all. So as we saw previously, so this is the model which we have considered in VisualSim architecture. So what I'm doing is um, I'm fixing my TG data whatever it generates data is to be 1024 bytes. Um, so I'm saying it will always generate 100% read, or it will always generate 100% read, or it will always generate 50% read or write mechanism. So that why I'm doing by selection here input a dot command. So either if you want to read, so you just make it equal to read, it will always generate read. If you want to make a write, it will always generate write only if you equal to write, or 50% read on write by using this command. So as of now, here what I'm considering in this scenario is input.a DRAM1. So and here DRAM2. So here DRAM3. So what it means, it's a no conjunction model here I'm having. So that is a different test, and this is one test. So what we are observing here, I fixed my 1024. What I'm varying is I'm varying my PCI TX and RX buffer sizes. What happens when I generate transactions from TG1, TG2, TG3? And moreover, in this scenario, I'm considering it can route to any of the transactions. The TG1 transaction, it can either go to DRAM1, DRAM2, DRAM3. So anyway, similarly for traffic 2 also, similarly for traffic 3 also. And next one is conjunction scenario. So in this, what I'm doing is I'm selecting all the teams and all are generating transactions to only to DRAM1. So in that scenario, what happens? And next is a no conjunction scenario. So no conjunction is the present situation is known. So traffic one, TG1 is always routed to DRAM. TG2 is always routed to DRAM2. TG3 is always routed to DRAM3. So I'm going to simulate here no conjunction scenario here. So no conjunction scenario will give us best throughput, best latency, and a better utilization of DRAM. Consider it as an ideal point-to-point communication scenario. In this scenarios, we get better values or optimize or higher best cases values. So what you are referring to here is it's a TG2 processor data structure details. So it's just generating some random address, uh, so this A byte. So I'm saying this is my TLP. So 236 bytes is what it is, and it has generated write command. So my write is and destination is IO name 2. So here IO name 2 is nothing but DRAM 2. So my TG2 is generating transactions of DRAM 2 of what write command, and of how much by 236 byte. So and here it is the port selection. So from port 2, it is routed to port 8. So from that, what I get here is my last few of the arguments like PCIe bytes is 236 bytes. What was its original? 1024 is original. What is a PCIe message? So read data. What is previous? It's a no op. No condition. So what is my task latency? So what it took. So task latency is generally, if you see, So I've issued a transaction here. So it goes PCI bus, it goes to DRAM, from DRAM back, it comes here. So this is my text to display. So my task latencies point so 32 into 10 power 12, 32 10 power 12, whatever. So that much is the latency. And similarly, my throughput array is this much. So, so these two are the parameters that which we generally look at into. And here the time array. So my DRAM, it went here at 0.45 microsecond, and it came out at the time of 0.61 microsecond. So the difference is the time consumed in DRAM in and out. So the operation of this. And similarly, from PCIe in to out. So it's very few milliseconds. The difference is very few milliseconds. So this is like this. We get a whole throughput like from issuing. So the time from 43 nanosecond it has started issuing the transaction. So next issue happened at 50.25 nanoseconds. So what is my so 7 nanosecond difference or something like that? 7 nanosecond for each 7 nanosecond. That's what here. So I'm configuring it here, right? TG2. So some value. So it generates that much TG rate or whatever rate. So it is issuing at this rate. Similarly for TG1 also, same kind of read or write transaction. What so and moreover, you can specify also how many transactions you want to issue here. Here is maximum, so you can just issue 10, 12, whatever you want to mimic it here. So, and one more thing, what we look at it is so this is PCIe stats, PCIe DRAM, this architecture here, this block stats. So this architecture setup, right? So this one stats we get here. So what is my DRAM utilization? So it's 100% utilized. Since it is my no conjunction issue, so TG1 is always transferring to this one. And similarly, DRAM utilization is this, DRAM utilization is three, and my delay time is this much. My throughput I'm getting here 108,544 Mbps value. And similarly, DRAM throughput, I'm observing this match, and DRAM 3 also I'm observing this match. And here PCI switches, since I'm using only 1, 2, 3, and 7, 8, 9. So what are the drop counts? How many transactions got dropped? And how many, what is my RX rate, TX rate? So if you generally observe, so yeah, we'll get a very high throughput rate here. So the TX is almost 90160 and RX is also 88 Gbps and here 90 Mbps transmitted. So all the ports are having best throughput or better band, better throughput rate. So this is since it is a low conjunction, we are observing this thing. So in general, there is one more stat also. So this one more is a PCIe debug. So what is happening inside PCIe bus, or what is happening, what this model is doing. So it is getting at 0 picosecond, what and all like initialization, what is happening, what is not happening. So at 636 because, or you can say at 0.63 nanosecond. So my PCI port one, it got received a transaction from TG1. So it is saying my destination port is 7. I have received 4 TLPs at this point of time. And I'm saying each TLP is 236. I am converting into flit. So it's a flit is a generally composed of multiple TLPs, right? So as we saw in this block diagram. So in general, I just give you basic what this flit means. So flit is this is 236 byte plus DLP plus CRC plus ECC. So again, this flit is having idle flit, no flit, payload flit, and all this stuff. So each TG or each port is having its own flit ID numbers getting issued. Similarly, for port 3, I received 3 TLPs, and for port 2, I received one TLP, and routing destination is this. These are the transactions that. So once you're issued, it gets subtracted from the transmitter side. So for 16 3 to 4 minus whatever that buffer usage. So it has used this much buffer for that endpoint one. So coming next issue is after next split distance. So at 7 it got received. Uh, It's saying fit disassembler PCI switch, so it received that whatever transaction it was there. Similarly, a port 9 received the sent, port 8 also it received, and there is acknowledgement also getting sent back. So that thing I've captured somewhere. And sometimes it even gets a no op packet. There is nothing, no transaction, nothing. It gets sometimes no op. See, number of acknowledgement. So it received acknowledgement for the flit number one. So flit number whatever I had sent from port one, it got received acknowledgement one. So similarly for port three also, for port two also. So whatever transaction I had sent, it received acknowledgement for that transaction. So uh, a few of the transactions they are getting dropped also because the buffer is not present or the values. So, uh, so here it's saying I have my receiver buffer usage is this much for this port, even similarly for port 9, my receiver buffer usage is. So at the end of the simulation, what we look at it in general is this much. So for port 2, so my receiver buffer usage is 64, my TX buffer usage is this much, and retry buffer. So this retry buffer usage is this much. So how many, whenever we issue a transaction from the transmitter, we generally store it in the retry buffer space. So this I've kept it 1024 just to be like whatever TX is getting issued 1024 bytes. I'm matching that to the retry buffer size for the best case. So here, so what it is saying is I'm just using 512 at the end of the switch. Here also 512, and here also 512. Here also. This is the best use case. So that's why we are seeing only 512 case. So, but if you refer to the other test scenarios or something, then we have a very high usage numbers and all. So hence I kept it 1024. So next, if we consider, let us consider 100% read. Um, so in general, what I've done is so just to have a parameter display or something like parameter variation and all. So just to have a batch mode simulations and all. So I have generated like these log files. I've saved them, and all of them have dumped into one directory. From there, I'm just extracting all the values from it. So this is just a summary. So what do I do? So this is task latency for 100% read. What is my task latency at the end of the simulation? So I'm observing these values. If you see, as I'm go on increasing my buffer size, so for one buffer size when I increase, for few of the TGs, it got reduced. So TG3 it got reduced. TG2 there is no variation. TG1 also no variation. For few test scenarios, my latency got decreased. Coming to throughput also same. So as I'm go on increasing my buffer size, my throughput is getting decreased. But when I make it still increase, so for 1634 it is seeing very high. But if you very good throughput and best latency. But when we consider again the same simulation for 100%, right? So there is no variation at all. So in the similar way, when I consider 50% read or write simulation, so if you see my task latency, best scenario I'm observing at 2048 and even at 812, 812, the slight difference between 4096. But wow, even the throughput is also better at 81192 and at 16324 it's constant. So even for 4096 only it's constant for TG2 and TG1 is also constant. Only for TG2 slight variation. So like this I've captured for DRAM utilization, all these stuffs. So next is 50% read or write scenario here also. What is the latency plot I'm observing? What is the throughput plot I'm observing here? So all of these scenarios uh, have considered. One is no conjunction, one is conjunction, and all of this. At the end, I am observing this conclusion. So once I fix my fixed TG, I'm generating 1024 bytes constantly, and I'm weighing only PCI TX RX buffer size. So I'm having this test in a 100% read, 100% write, 50% read or write. So what I'm varying is my TXR buffer size from 256 to 1634, and my replay retry buffer I've kept 1024 because in my write transaction I have observed that 768 or 800 or 850 I get that many retry buffer getting occupied in that usage or buffer usage stat, right? So I'm seeing that much. So these are my conclusions. So what I'm saying is I need 4096 is the strong buffer size, and my retry buffer I'm saying 1024 is needed because max usage is 768. But When we observed for 50% read or write scenarios, we will be getting only 512, but best use cases better one. So 1024 is the best one. So similarly, I've kept for the conjunction scenario. So in general, conjunction scenario will be the worst scenario, and no conjunction scenario will be the best scenario. So if you consider these two scenarios, in this, if you consider 50% read or write scenarios, so in conjunction scenario, so I'm same scenario. I'm TX buffer from 1024 to 62. So I'm saying my latency is best at 4096, and throughput is also better for 4096. And once I start to increase my buffer size, so there is a slight increase in the throughputs and all, but which can be better, only slight like 5% or anything. So 4096 will be the best one. Even similarly for no conjunction point to point also, TG1 is generating transaction to DRAM, TG2. So this is like point to point one. This will be the best scenario. High throughput and low latency, larger buffers will improve the performance. So here is the best point to point. So based on these scenarios, I'm fixing all of the values like the my best PCI buffer size should be like 4096 bytes, retry buffer size should be 1024 bytes, and MRSS conditions for this MRSS is nothing but max read request. This has to always match to the generating TG size. If it is less than that, it means it cannot accommodate that thing, or it throws an error in general. So so I've seen that scenario also, and few of the scripts whatever I have written just to extract the values and all those stuff, just to populate the things. Um, so here, if you observe for few of them, so what is my drop count? So this is one scenario. So like this, I've captured for all of the stats and I've just plotted it in normal Excel sheet or something. Uh, so this is my basic system validation of the PCI, what I have considered. Uh, this is very small model, basic model like for PCI bus validation. So that's all like what is my throughput, what is my task latency, what I'm observing, if I give my 50% read or write transaction, and what if I make 100% read or what is 100% write, how much throughput I observe in my model and all these stuffs. If we come to these values, right? Huh? So, for example, let us consider this is a test scenario 100% right. So 100% right. What I'm seeing, what I'm observing for port one, what is my TX, what is my RX receive throughput values. So for port one, so these are the values. I'm seeing better usages for 4K or buffer size only. Similarly for port two also, better values at 4K. Even for port three also better values at 4K. If you if you consider, for example, no, I'm observing for 1024 itself uh, better value for 100, like for 100% right case, right? So even for 1024, I'm getting best here. This is the best. This is the best. There are other scenarios also based on that. We are fixing 4K should be the value or something like that. So here also, if you compare for port 8 or port 9, so each one, based on the scenario, it is. And in the model, we don't have for each port fixing or anything. This is like in general, it applies for all the ports. So this is the 12 device connection scenario, like transmitting from here to here. Uh, next, one more plot. What I have. So same, what is the DRAM? In general, the DRAM utilization should be less. So as you see for buffer 4096, I'm observing my DRAM utilization is 81. If you go for higher 812, it's less like 61, 74, even for best I'm observing at 16K, but it will be of very huge buffer size and all. So not going here. Since it is only 100% right, so we are observing better utilization here. That's all.